your ability to choose the right statistical test. Because if you cannot choose the right statistical test, most often you end up doing um, a statistical test that is wrong, which is not acceptable. So we're going to start right away now. We'll look at normality test. So I'm going to share my screen. So can you see my screen?
Yes, I can see it.
Yes, I can see it.
Now, like I said, what we are going to be looking at today is assessing normality and transforming data. But basically, what we really mean there is the aspect of assessing normality. So now, we want to look at the role of normality test. Now, when we talk about normality test, we know that many statistical methods require that the numeric variable that we will be working on, that we are supposed to work on, we have an estimate of normal distribution. So when we are talking about normal distribution, we're actually talking about a data set that is distributed equally to some extent across board, that we have less data as the left hand and the right hand side. Then we have more data at the center. So we have kind of something that look like a dome shape. So this is actually what we are talking about. So you can see here that let me hide this. You can see here that the data here are few. The data here are few. Then as they are coming up, then they are building up. They are building up. Then until they get to the center where you have a large data set. Now at this end, you will have over 95% of your data. Then here you have about 95, 99.7%, 95%, then 68%. So what we are saying in essence is that from here to here, you will have this distribution of your data. Then from here to here, then we have another set of data. Then from here to here, we have this category of data. So basically, when we talk about normality test, when you draw an histogram, this is how a an histogram of a normalized data look like. So meaning that if you should draw uh, a histogram of your data set and it doesn't look like this, then that data is likely not to be normally distributed. Now, example of tests that require numeric data, like we said, we have the t-test, then we have the f-test, which is also referred to as ANOVA, then we have the regression. It means that at any time that you want to use any of these test category of tests, you must do normality test on them. You can you cannot assume. You must test the data to be sure that they are normally uh, distributed. So
Distributed.
that is a very um, important aspect that we need to understand. It is very, very uh, essential. So now the next thing that we want to also talk about is that now we want to look at things that you can use to assess your normality. What are the things that you are supposed to check out for? when you are doing the normality test, what are those things that you are supposed to check? Now, the first thing is that you check the histogram and the bus plots. We are going to look at all of that. Look at histogram and bus plot.
Plot.
Yeah. Then the next thing is that you look at you also check normality quartile plots. Although we don't really use that. That normality quantile plot is also referred to as normality probability plot. Then the next one is that you do what we refer to as goodness of fit test. Now, this is actually very, very essential. In this goodness of fit test, we have two types. We have the Shapiro weak test, GM. That is usually used in a software called GMP, although we also use it in SPSS. Then we have the Chirovi test. That is actually what we refer to as KS test. Then, meaning that there are two tests that you usually do in SPSS. You do SW test, then you do the KS test. Now, if you are using a mini tab, which is also a statistical software, you will do Anderson dialing test. So we are not doing that because it's not within the jurisdiction of this study. Now, when we talk about bus plot, we are talking about this is an histogram. This is an histogram. And this is a bus plot. Now you can see that this is actually a cholesterol level of male heart patients. We're talking about the cholesterol level of males heart patients. So now you see that in this scenario, we have two types of line here. This line. Then you can see that this plot is more like the one I showed earlier. I mean, this particular one. Yes, it's more like this. So this one is actually more like that. Now, this is the bus plot. Now you can see that the red curve represents a normal distribution fit to this data, and the blue curve show the density estimate for this data. So it means that the red line is actually what is showing the normal distribution, while the blue line is trying to show the density estimate of the data you are looking at. But basically, when you are doing a real life situation analysis, you will not be using two. It's just the only one. When we are going to look at it, when you go to your data set and you click on it, then you can add them to add this particular line. Then you will see the line added to it. Now you can see that this bus plot, in as much as this bus plot is within the center, but you can see that it's not a perfect fit. If it was a perfect fit, it would have been at the center, at this center. But you can see that it's kind of away a little as the case may be. Now, this is another bus plot and also histogram. Then you can see that this histogram or the bus plot is tending towards the upper part. It's not at the center. And you can see dot. These are what we refer to as outliers. When we say outliers, we are talking about extreme variables, data that are extreme, data that are either too low or they are too high. So it means that extreme variable can actually be two. It could be a high value or it could be a low value. That's why most time when you are doing your quality control in the lab, when you see they are referred to as critical values in the laboratory, they will tell you that when you see critical value, when you verify and you are sure that they are critical value, you are supposed to want to communicate them. Even though the doctor is supposed to send somebody, or you are supposed to send somebody to go and to go and give the test result to them, whatever the case is. But when you are seeing an extreme value, what do? Most times you pick up your call and call the doctor and report the case to the person. For example, you are seeing a patient that you are seeing a glucose level of like 2.1 milligram per day. You know that is a critical value. Or you are seeing 20.4 milligram per day. You know that is also a critical, extreme or
Well,
critical value. So when you are analyzing analyzing data, and you have those kind of extreme data in your data set, they will usually present you with this kind of box plot. Then you will always have this extreme value. Now, one of the ways to deal with extreme value is that when you check and you are not sure whether it was rightly entered or not, then the rule of thumb is that you remove the what is it called? You remove those extreme value and rerun your data. But when you check and you see that they are actually normal, they be tested, they be checked, and everything is normal, what do? Then you go ahead, and that's what will now make you to know that, because once you have a normality plot or distribution like this, automatically you cannot run a t-test, you cannot run ANOVA, cannot run regression on them. So you will not do what we refer to as non-parametric test. Are you getting me? So if you have something like this, then you'll be going for parametric statistic or parametric test. But when you have something like this, you'll be going for non-parametric test. Now, I've mentioned that already. Now, I mentioned here outliers are usually not consistent with normality. So it means that at any data set where there are a lot of outliers, that is already a pointer that data is not going to be what? It's not going to be the normal distributed data. Now, the next thing that we'll look at, this is how your normal quantile plot look like, or what we also refer to as probability plot. Now, basically, you can see here there are few data here. All these dots. There are few here. Then you can see a lot here. Then you see few here. So that's what brings about this kind of a dome shape. Now, if data is approximately normally distributed, we should there should be spacing. The spacing differences between them should be similar. It therefore means that the differences between here and here should almost be the same. But if they are not normally distributed, you see some kind of data. Now, some things we need to note here is that important note is that if your data, your plot data versus normal data are on the previous as we have seen, you can see that downward bend is equal to left skew. Now, what we are saying in essence is that if you see downward bend like this, it is, we refer to it as left skew. But when you see upward bend, for example, you see an upward bend like this, so this is left skew, and this is right skew, as the case may be. So that is basically that. Now we want to quickly take an example now. Now, assuming we have a data set, there are several. I hope this lady is here.
I'm listening.
So there are several tests that there are several parameters that we can run normality test. Now, this example that I want to do now, these are the steps that you are supposed to take when you are testing for normality. The first thing that you will have to do is to what? Is to state your hypothesis. Now, remember I mentioned that we have two types of hypothesis. The first one is what? Is
Null.
null hypothesis. And null hypothesis is, in this case, is that the data distribution is normal. That's the null hypothesis. While the alternate hypothesis that the data distribution is not normal. Now, it therefore means that when you run your normality test and your data is normally distributed, what will you do? You will accept the null hypothesis and reject the alternate hypothesis. But in the sense that your normality test is not normally distributed, what will happen? You will reject the null hypothesis and accept the alternate hypothesis. So let's dive into it. Now, common test of normality includes, we already said, SW test, then KS test. So we'll talk about the Anderson is not for us. Then the problem is that most times both SW and KS is usually not, they don't agree. But in some cases they could agree, but in most cases they don't usually agree. That's why you don't just only do normality test, use SW and KS test, and you go and sleep. So you have to correlate it with other form of test. For example, like you have to look at the histogram, you have to look at the box plot, you have to look at the quantile plot, the distribution, and all the rest, or what we refer to as the probability plot. So now let's dive into this. Now we want to use the example of this. This is the what we want to use as an example. This systolic volume of a male heart. That's what we want to use for this example now. So let's go there. Now, we are saying that the distribution of systolic volume is normal. That is our null hypothesis. While our alternate hypothesis is that the distribution of systolic pressure is not normal. Remember that systolic pressure is a continuous variable. It's not it's not a it's not nominal, it's not it's not ranked, it's not ordinal. It's actually what is continuous or interval ratio kind of data. So it shows that there are two tests, there are two set of data that you can actually run normal, that you can major test that you can run normality is the data that is numeric, that is what continuous. Now the next thing is that these are the parameters. Now after we run our normality test, this was the outcome we saw. The first outcome here, you can see this is the box plot. You can see that the box plot is not at the center and there are outliers. Then when you also check the what is it called, the histogram, you can see that the histogram too is not what tallying with what, it's not tallying with how a normal distributed data is. But you will not just base your conclusion on based on those two. Then you have to come and check the fitted normal, which is this in this case, these other parameters. We have the mean parameter, we have the estimate, then we have the 95% upper, then 95% lower. These are 95% confidence interval. No, we usually have two values in 95%. We have the lower value and then we have the upper value. But that is not also really where we are going. Where we are going next is this goodness of fit test. Now, if you look at the goodness of fit test, in this case, they decided to use the SW test. Now, you can see that the SW test is telling us this is the value that the SW is telling us. And the SW is telling us that the value is 0.825 and the p-value is less than 0.05. Now, Remember that when you have a p-value that is less than 0.05, it means that that data is statistically significant. It differs significantly. So, in essence, what this is telling us, because the p-value here, I need you to note this. Note that the value is from is not. This will be that the data is not from normal. It's not from normal distribution. So small p-value, then you will reject the null hypothesis. What we are saying in essence is that at any point in time you have a significant p-value and it also correlates with all these other parameters, then you will reject your null hypothesis, because your null hypothesis says that the data is normally distributed. That's what the null hypothesis states. But in this case, small p-value rejects this, because small p-value means that it is not normally distributed in this case. I don't know if that is clear. So meaning that when you run your normality test and you have a significant p-value, what do? You reject null hypothesis. But when you have a value that is not statistically significant, let's say the p-value was 0.6, 0.7, 0.08, 0.09, 0.1, but it's not less than 0.05, then if the data was like that and all these other parameters also holds, then we would have accepted the known hypothesis. But in this case, we would reject the known hypothesis because p-value is less than 0.05. Now, the next thing that we want to look at is, okay, I already mentioned that because p-value is less than 0.001, we have strong evidence against normality for the systolic volume population distribution using the SW test. Now, let's move forward. Now, you can see that using that same data set, remember we said that SW test and KW test most times does not agree. So if you look at this, setting the same hypothesis, then running this SW test, you can see that the p-value was not significant, because this is the p-value. This is 0.058 because it's greater than 0.05. So if we have to follow this particular test, this test is telling us that it's normally distributed. But we know that merely looking at it, these plots have already told us that it's not normally distributed. So in case when you run your normality test and you're having this conflicting data set, then you make sure that you run the SW test to confirm. If it's the SW that is giving conflicting outcome, then you run the SW to check. Then you also check with your box plot, you check with your histogram, then you'll be able to make a conclusion. So, like I said, you will not accept this one because it's not correct. Now, the next thing I want to look at, cholesterol. This hypothesis is saying that the distribution of cholesterol is normal, while the known hypothesis says that the distribution of cholesterol level is not normal. Then what we will do now? This is our data set. Now, merely looking at this data set alone, we already know that this data set is normally distributed. Then check what did you say? Hello?
Hello.
Yeah, are you following me?
Yes.
Yes.
Okay. So I was saying that when you look at this particular data set, you can see that the box plot is almost normal, although there is an outlier, but this outlier we're not really able to impart. Then if you want to be sure very well, then you can remove this particular data and rerun your normality. You see that it will be more better. But even looking at this normal, you can see that this data actually meet the requirement for normality based on this box plot, based on the history. Then we also come and check the goodness of fit. And see that the p-value is 0.218, which is greater than 0.05. So in this case, we are going to accept the uh, we are going to accept the non-hypothesis, which states that the distribution of cholesterol level is normal. It therefore means that
Distribution normal.
therefore means if we want to follow this particular instruction, therefore mean that we have strong evidence to accept normality. So we have strong evidence to accept normality because
Yes.
all the 3 different tests that we are supposed to do, all of them passed. It's just like running your QC. Usually we have your low value, your high value, then sometimes you even have your medium value and the case may be. So just imagine your low value, your medium value, and your high value passing your QT test. So you are so confident to release what your result because you know that it cannot be questioned. So is that okay?
Yes.
Yes.
So here we have no evidence against normality of the population of distribution of cholesterol for me. So therefore, we will accept the non-hypothesis. Now, there are some other things I will just mention. Usually, when you run data and the data is not normally distributed, it's not normal. It's not normally usually. Uh, there is actually a remedy that you are supposed to do, which is you transform the data. But the truth is that in practice, that does not work. Once your data is not normally distributed, the next thing is that you remove parametric test out of your mind. Then you focus on what? Non-parametric test. So I will stop here. Then I will take your question. Then before we move to the next, that's the choosing of statistical test. Then by tomorrow, when you must have downloaded the software that I pasted on the WhatsApp group, then we can start live demonstration of all these things that we'll be talking about. So,
Hello, sir. Hello.
yeah, hello.
Okay. I want to know that what you sent on WhatsApp. Can one use phone to download it? It's a software.
No, it's better you use your laptop.
I've tried using laptop, but I didn't succeed in downloading it.
It's heavy. It will take time actually. It's about I think it's about
Okay.
Yeah, I'll do the result. It's coming. All
the
right, sir. Man is family. You know, feeling fine.
Did you get me? Hello?
Yeah, hello.
You said?
Yeah. I said
You continue. Oh,
it's about 300 MB, so you need to use your system to download it.
okay.
Ah. All right, sir.
Or you don't have
There's nothing
Flourish, you
there.
don't have system.
My system
What you
crashed,
do?
so I've been waiting for the program.
Ah. So what are you going to use now?
Hello?
What are you going to
I'm
use?
planning on getting another one. I'm planning on getting
Okay.
another one. That was why I was asking for the flight.
Yeah, I
Hopefully,
will
end of
send the
this month, I'll get another one.
Of course, the videos are also going to be available, so you will watch
Okay.
You can replay and then what about birthday? Your own system? You have your system, have you?
Yes, I have, but like I told you, I've tried downloading it with the system, but that thing didn't go through. Now I will still try again. Sha.
Just let me know if that link, in case the link is not good, then I will know. Okay, just to be sure, let me go and try up the link. Let me see what. And this is the link. It's working now. This is something like this that will come up. Are you with
Yes,
me?
yes,
Then you now
yes.
click on. You click on what? Download. Are you
Download.
hearing me? Yes.
Yes.
So it should download. All right. So where were we? So any question from your end before we dive into the other? At least you understand what normality now. When I'm mentioning normality in this aspect now, then you'll be able to cope.
Yes.
Hello?
Yes, can you hear me?
Yes, I can hear you.
Any question?
I wanted to. You said this class that we do now is to test data normality, right? Hello, sir.
Yes, yes.
Okay, data normality. All right. Because I wanted to um get what you were actually saying. Because I've heard of the null and the is it alternative hypothesis? So and that's a distribution.
Mm.
Yes,
No,
it's
it's not
something that we.
only in distribution. Even by the time we'll be, I mentioned that we have two types of statistics. We have theoretical and applied. And under applied, we have uh, descriptive and inferential. Then when we are going
Yes,
to
sir.
be talking about inferential statistics, you're going to see that um, you're going to see that under influential statistics that we actually be having what's it called? We'll be stating a whole lot of hypotheses. For you to be able to make influence, you have to state hypothesis because the hypothesis you are going to be testing. Is that clear? So you
Yes,
have
sir.
to state hypothesis.
Yes.
Even for example, now in your thesis or during your masters, you can, for example, let's say you can say the HB1C of type 1 uh, TB of type 1 uh, TB, sorry, type 1
DM,
um,
DM.
DM rather, is
Okay.
significant, is the mean value of the uh, HB1C of type 1 DM is statistically uh, different from that of what's it called? From that of type 2. That is
Type
an
Alright.
2.
hypothesis. Yes. Why the non-hypothesis is that it does not. Are you with me?
Yes.
Yes.
So in this case, so what do? You have to now test. You collect data from DM and you collect data from non-DM. Then you what? You you check for their normality. If they are normally distributed, then you run, since there are two groups, type 1 and type 2, then you run your t
Yes.
value, your t test rather. Then if the p value is actually statistically different from that, then you accept your what? You accept your non hypothesis. But if it's not
Hypothesis.
statistically different, then you reject your non hypothesis, which states that is differs, while the alternative say is not differ. So that is just at every um, test that you're going to be running, you must set hypothesis. Is that clear?
Yes, sir.
Yes, sir.
So
So
this
let's
is
look.
this is an example of inferential statistics.
Yes, influential. Then descriptive statistics is just saying that of uh, the mean value of HB1C of type 1 is so and so. The mean value of HB1C of of type 2 DM is so and so. You are not saying that is this one is bigger than this or smaller than this. You are just stating this is it. Or you say the mean age of the population is 12.5. The mean age of the pregnant women is 15. It cannot be 15. Let's say 25. Then the mean age of the pregnant women from the rural area is 26 point. So the mean age of the pregnant women from the urban area is this. You are only describing the data. You are not inferring anything from the data. I don't know if that is clear. You are not making any influence. You are saying the percentage of people that have you are saying that the percentage of children under 5 that have malaria in Nigeria is this. You are not making, you are only just stating the value. You are only describing. Are you getting me? You're only
Yes.
describing. That's why most times during undergraduate and postgraduate, when you submit your data to your supervisor, especially in chapter 4, they will tell you that what they need from you is for you to just describe the data. Don't chapter 4 is for you to describe the data, not to make influence. Don't deduce
Inferential.
influence from it. It's actually you just describe the data, then you compare using statistics. Then when you are using statistics to compare two groups, it's no longer distinction, it's now differential. You are now making inference from it. Is that clear?
Yes, sir. Thank
Yes.
you so much.
Yeah. Yeah. So let's switch to where we left off yesterday. So basically, this is what we want to. I guess this is what we were talking about.
Yes, sir.
Now we've understood what normal
Population.
distribution is now. So it's time for us to now look at now. So we have a population. Then the population, we have one sample population, we have two sample population, then we have three or more sample population.
Population.
Now, I said when you have a one sample population, and the description I gave regarding one sample population yesterday was that when you have an established value or reference value that you intend to compare the mean of the value of the derived value that you want to compare. Now, what I'm saying in essence, like I mentioned yesterday, we have a reference value for cholesterol, for example. I think it's less than 200 milligram per DL. Now, that is a reference value. That is an established value. Now, you are now running, let's say you are running the cholesterol level of athletics, sportsmen in your state. You collected their blood sample, uh, um, you've analyzed them, you've gotten the cholesterol level for all the sportsmen in your locality. Then you now want to compare the mean value of the cholesterol level of your sportsmen against the standard value, the reference value. Now remember that because it's only just the sportsmen you are looking at, that sportsman is only one population. Are you getting me? So
Yes.
for you, the next thing that you need to do for you to know the type of test you are going to run, that will take us to where we just landed from. You run what we refer to as what? Normality test on it. Now, once you run your normality test and it met the criteria, then you will now go and run what we refer to as one sample t-test. But when you run your normality and it does not meet up, what do? You run what we call Wilcoxon rank sum test, which is an example of what? Non-parametric test. Now, this one sample t-test is a parametric test, a parametric statistic, a parametric statistic analysis test rather. Why the Wilcoxon rank sum test is what we refer to as what? Non-parametric test. So non-parametric test is done when your data is not normally distributed, when it does not meet the requirements that has been set for normality. Then you run what we refer to as non-parametric test. Now, moving from there, we'll go to the next sample group, which is the two sample population. Now, these two sample population, the same cholesterol that I was talking about, but in this case, it's still sport people that you want to examine. But in this case, you are looking at, you want to compare the cholesterol level of sport men against sport women. So in this case, you collect sample from male sport men, then you collect sample from sport women, then you determine their cholesterol level, then you now also come and run normality test on them. You run normality test on the women, on the male category, then you run parametric test too on the female sportsmen. Then if they are normally distributed, then the next thing that you have to do is to ask yourself, is it a paired test? When we say paired test, let's assume you're only looking at just only sportsmen and you collected their cholesterol level in first quarter, and now the same, let's say 20 sportsmen collected their cholesterol value at first quarter of the year, then in second quarter you now you collected another cholesterol value. Now you remember that although they are one group, but you are collecting their sample in two equal sets, so they are actually pair because they are correlated, they are related. So if they are related, then you will run what we refer to as paired t-test. But if they are not related, like the sportsmen and sportswomen, then you run what we refer to as what? Then you now ask the next question: are they equal variance? Most times they will never be equal variance. Then if they are equal variance, you run what we refer to as unpaired t-test. Then if they are not equal variance, you run what we refer to as wedge corrected unpaired t-test, which is also referred to as two sample independent t-test. Now, the next thing is that if they are more than, if they are not normally distributed, then the next thing that you add yourself is if they are also paired, then you run what we refer to as Wilcoxon matched pair test. Then if they are not paired, then you run what we refer to as what? A Mann-Whitney test, which is both these two, both the Wilcoxon match test and the Mann-Whitney test are actually non-parametric. While the pair t-test, unmatched pair t-test, and wedge corrected paired t-test are parametric tests. Now, if you have more than 2 or 3 sample, a group or population, now the next thing that you do, you also collect sample, then you ask yourself, are they normally distributed? If they are yes, then you come here, are they paired? If they are paired, you run what we refer to as repeated measure one way and over. Then if they are not paired, you run what we refer to as one-way ANOVA, the most popular one-way ANOVA. Now, if they are not normally distributed, then you also ask yourself, are they paired? Then if they are paired, you run what we refer to as Friedman test, which is an example of non-parametric. Then if they are not paired, then you run what we refer to as Kushner-Willis test. Kushner-Willis test. So those are actually the kind of tests that you can run. Now, let me just take you to somewhere. Yes. Now, here is another thing. Remember that we have two types of data. The one I described so far are what? Continuous data. Now, in the event that you have, are you with me?
Yes.
sir.
In the event that you have categorical or qualitative data, then you will be talking about either chi-square, relative ratio, or logistic regression. No, in this case, for qualitative data, you don't run normality test on them. You only run normality test on what? Numeric data, continuous data. So that is what I just want to bring to your notice. So any question? Is it okay?
So far, I don't have any question, but I think when we start
The
applying this
practical,
thing,
yeah,
the
yes,
practical, I will assimilate everything. Uh,
yes. So
so,
this is where we'll end this class. Then we'll continue tomorrow with practical session. So please, I really appreciate your class. You've been keeping to time. So let's continue like that. If we go with this speed that we are going, we can finish up even by Sunday. Then you'll be practicing. And when you have any issue, then you bring it up to the WhatsApp group, then we discuss it. The truth is that no matter how long I'm going to take to teach you, if you don't practice, you will forget it. So when you keep
Exactly.
practicing, you keep making mistakes, then you keep getting correction, then you keep developing yourself. Then when you have learned this first aspect now, then you can now say, okay, I've understood SPSS. Then you now move to other kind of data too, like your Tableau, your Power BI, your arrow programming, then your Python and the rest. Then you
okay.
look at SQL and the rest. But these are the foundation. You need to understand this foundation. So it's when you understood this foundation, then you can now build upon this foundation that you already had. So it's very essential that you have a very solid foundation. So this is where we'll end the class for today. Then we'll reconvene tomorrow, God helping us. Then
Okay.
yes,
Okay. I will try and download that the software you sent to us. But
yes.
if I didn't
So
succeed, maybe by tomorrow, or I will